All right, today we are looking at SkillRL, Evolving Agents via Recursive Skill-Augmented Reinforcement Learning by Peng Jia and colleagues.
Yeah, this one's a big deal.
It really tackles this amnesia problem you see in a lot of LLM agents, where every single task is a fresh start, like it's learned nothing from the past.
Exactly. And the old way of fixing that was just to, dump raw interaction logs into a database. Things like mem0 or expel.
Which just bloats the context window. It's all noise.
Right. So SkillRL comes in with a totally different approach. It tries to bridge that gap between just raw experience and actually improving the policy.
No.
It distills those messy trajectories into a clean, hierarchical skill library. They call it the SKILLBANK. And then, this is the cool part, it uses something called recursive skill evolution.
Meaning the library and the agent, they grow together.
They co-evolve, the agent gets smarter, and the library gets richer, all during the RL process.
And the results, they speak for themselves. State-of-the-art on ALF World with an 89.9% success rate. WebShop, 72.7%.
And the craziest part is the model they used.
Qwen 2.57b, a 7 billion parameter model.
A 7B model that is outperforming massive closed-source models. We're talking GPT-4o, Gemini 1.5 Pro. On these really complex agent benchmarks.
It's a huge signal that maybe how an agent learns is becoming more important than just how big it is.
It's about abstraction, not just raw memory.
Okay, let's back up and really unpack that core problem. We said amnesia, and the typical solution is RGE, right? Retrieval Augmented Generation. You give the agent a database of its past actions. Why isn't that good enough?
Well, it really comes down to the signal-to-noise ratio. If you look at the standard methods, React, reflection, you name it, they store the raw trajectory.
The whole log.
The whole thing. The observation, the action, the reward. The OAR tuple over and over.
So my agent wanders around a virtual kitchen for 50 steps, opens a bunch of empty cabinets, then finds the apple. The memory saves all 50 of those steps.
Exactly. And that's just, it's incredibly inefficient, it's so verbose, and it's full of noise.
And you're trying to cram all of that into the context window for the next task.
You are. And the model has to sift through, I opened cabinet A, it was empty. I opened cabinet B, it was empty, just to find the one useful bit of logic.
So you get this trade-off. Either you save everything and your compute costs go through the roof and you confuse the model, or you cut the log short and maybe lose the important stuff.
Right. And the Skiller authors argue this isn't how people learn. An expert doesn't memorize every single keystroke from a debugging session.
No, you abstract it. You learn a rule.
You learn a heuristic. If the error is X, the first thing I check is variable Y. That's a skill.
So SkillRL is basically an architecture designed to force the model to do that abstraction, to turn the raw footage of its life into a concise rulebook.
Precisely. And to do that, they use a teacher model. In the paper, it was OpenAI's O3, which acts as a critic, looking at the rollouts from the base model, the Qwen 2.57b.
Okay, let's get into that distillation process. Because in normal RL, you just care about the reward, win or lose. But they do something really interesting with the failures.
Yeah, this is one of the most clever parts of the whole framework. If an episode is successful, okay, the teacher distills that trajectory into a good strategic pattern, a how-to guide they call S+A.
But what about the failures?
It doesn't just toss them, it does what they call a counterfactual analysis.
A counterfactual analysis.
It looks at the failed trajectory and figures out exactly where the agent's logic went wrong. It basically says, okay, at step 5, you did action A, but the state was B, so you should have done action C. Synthesizes a failure lesson. An S.
Wow. That is so much more useful than just a negative number. It's like a teacher giving you an F versus a teacher writing a detailed note in the margin explaining why your argument didn't work.
And that note becomes a permanent skill in the library. So the next time, the agent doesn't just know, don't do that. It knows why not to do it and what to do instead.
So you're building up this collection of rules, the SKILLBANK. How is that thing organized? Is it just a flat text file?
No, the structure is absolutely critical. Otherwise, retrieval would be impossible. They use a 2-level hierarchy. At the top level, you have general skills. That's SG.
And these are the universal principles, the big ideas.
Correct. Things that apply pretty much everywhere, like systematic exploration. If you're in a maze, visit new places first. Don't just loop around. Or verify preconditions.
Like check if you have the key before you try to open the door.
Exactly. Stuff that seems obvious to us, but LLMs constantly forget to do. These general skills are always injected into the context. They're like a foundational common sense layer.
And the second level?
That's your task-specific skills, or SAMINA. These are for specialized problems. So in ALF world, you might have a skill just for cleaning objects. In WebShop, it could be price comparison logic.
And I'm guessing you don't load all of those into context every time.
No way. For those, they use dense retrieval. They embed the task description like find a blue shirt and do a semantic search against the skill bank to pull the most relevant ones.
And this whole setup is way more efficient, right? The paper had some crazy numbers on token compression.
Yeah, between 10 and 20 times compression compared to just storing the raw logs, like in a standard R-RAID system.
10 to 20x, that's massive.
It completely solves the context bloating problem. Instead of 2,000 tokens of I walked here, then I opened this, you get 100 tokens of to find the apple, check the fridge first. It's pure strategy.
Okay, so we have the library, we have the retrieval. But there's a really important practical step in here. You can't just give a vanilla 7B model a list of instructions and expect it to work, can you?
No, absolutely not. That's what they call the cold start problem. If the model hasn't been trained to actually use these skills, it might just ignore them or get confused.
So how do you bootstrap that?
They run a phase called Cold Start Supervised Fine-Tuning, or SFT, before the main RL loop even begins. They use the teacher model again, but this time to generate a data set of reasoning traces.
What does a reasoning trace actually look like here?
It's a full demonstration of the process. It shows the agent thinking, okay, here's my task. I'm retrieving this specific skill. My chain of thought is now referencing this skill. And based on that skill, I'm generating this action.
So you're literally behavior cloning the act of being a skill-using agent.
Exactly. You fine-tune the base model on all these demonstrations to create what they call the reference policy, PREF. And in the ablations, this was a huge deal. Turning off this SFT step dropped performance by like 20%.
Wow.
The agent has to learn how to use the library before the library can actually help it.
That makes so much sense. It's like giving someone a user manual. You first have to teach them how to read the table of contents.
And once that's done, then they move to the core of the paper, the recursive skill evolution.
Right, the recursive part of the name. So the library isn't just built once and then left alone.
Correct. It's dynamic. In most array setups, your knowledge base is static. Here, after every RL epoch, the system runs a validation check. It looks at the success rate for each category of task.
So it's constantly grading its own homework.
Yes. And if the success rate for, say, cooling objects drops below a certain threshold, it triggers the evolution mechanism. It grabs all the failed runs from that category and feeds them back to the teacher model.
And the teacher asks, okay, why do we keep failing at this specific thing?
Precisely. It identifies a gap in the skill bank. Maybe a skill is too vague, or there's a new edge case. The teacher then proposes new skills, or refines existing ones, to plug that hole.
There's that great graph in the paper showing the library size growing over time. It starts with around 55 skills and grows to 100 over the training run.
And if you look closely at that graph, the general skills, the SGG, they stabilize really fast.
Right.
Once the agent learns Explore systematically, it's done. The growth is almost entirely in the task-specific skills. The agent is building an incredibly specialized playbook for its world.
Okay, let's talk about the RL algorithm itself. They used GRPO group relative policy optimization. That's the one from the recent DeepSeek papers. Why GRPO here?
It's about efficiency and stability. A more traditional algorithm like PPO requires a critic model, a whole separate value network to estimate rewards.
Which means more VRAM, more complexity.
Exactly. GRPO gets rid of the critic. Instead, it just samples a group of, say, G different trajectories for the same prompt. It then uses the average reward of that group as its baseline.
So it's basically comparing the agent against itself in real time. Was this attempt better than my average attempt just now?
Yep, it's much lighter. But SkillRL adds a crucial twist. They include a KL divergence penalty to keep the model from changing too much, but they anchor it to that cold start SFT model we just talked about.
So you're not just letting it chase rewards anywhere it wants.
You can't. You have to prevent catastrophic forgetting. Without that anchor, the model might just find some weird reward hack and forget how to use the skill library entirely. This forces it to remain a skill-using agent while it gets better at the task.
It keeps the learning structured. Okay, so let's get to the payoff. We mentioned 89.9% on ALF World. That number is just huge.
It is. And for context, the vanilla GRPO baseline, same model, no skill library, only got 77.6%. So just adding the skill mechanism was a 12-point jump.
And against the big commercial models.
GPT-4o scored 75.3%.
That's the number that blows my mind. A 7B open model beating GPT-4o by nearly 15 points on a task like this. Where did the gains come from? Was it on specific types of tasks?
Absolutely. The longer the planning horizon, the bigger the improvement. In the pick two task, where you have to find two different items and put them somewhere.
A classic amnesia trap.
Right. SkillRL improved by 23% over the baseline there. In the cool task, find an item, cool it, place it, a 22% gain. These are exactly the kinds of tasks where raw memory just drowns in noise.
And it also worked on WebShop, which is a totally different domain.
Right. WebShop is all about search and filtering on a simulated e-commerce site. SkillRL hit a 72.7% success rate there, too.
There was that qualitative example in the paper that I thought was perfect. The one about the blue shirt.
Ah, the navy blue button-down one. Yeah, the user request was super specific. It had like 5 constraints. Women's, long sleeve, navy blue, size large, machine washable, and under $40.
That is a lot to juggle.
A standard agent just gets lost. It'll find a blue shirt but miss the price, or it finds the right price but it's the wrong size.
Or it sees the base price and assumes all sizes cost the same.
Which they never do. So SkillRL retrieved 2 key skills. One was a general skill, prioritize core keywords to build a good search query. But the second one was a task-specific skill called check variant price.
Check variant price.
The agent's chain of thought explicitly says, I must check the price for the large variant specifically. It navigates to that option, confirms it's under $40, and then clicks buy.
And the only reason that skill exists is because the agent must have failed at that exact thing before?
That's the recursive evolution. In an earlier epoch, it bought an expensive shirt. The teacher model analyzed the failure, wrote the rule, always check the variant price, and patch the agent's behavior.
It's writing unit tests for its own logic in natural language.
That's a fantastic way to put it.
I also love the ALF world example, no appliance before object.
A simple logic patch. The agent learned that running to the microwave before you actually have the egg is a complete waste of time. It sounds so basic, but for an RL agent learning from scratch, that's a hard-won lesson. This just tells it the rule directly.
It really feels like natural language is a super efficient medium for the gradient of learning, I guess. Instead of just tweaking weights, you're updating a rule book.
And their ablation studies back this up. When they turned off the recursive evolution, so the skill library was static, the model plateaued way earlier, it got stuck in a local optimum.
Couldn't improve past a certain point.
It just didn't have the skills, the vocabulary to solve the harder problems. The co-evolution was essential for breaking through that ceiling.
And they briefly mentioned this works on search-augmented QA tasks too, right?
Yeah, things like Hotpot QA and Trivia QA. It beat out Search R1 and Evolver, especially on multi-hop questions where you have to string together multiple pieces of information.
Which is really just another kind of plan.
Exactly. Skills like verify search result reliability or decompose complex query just gave it a more structured way to attack the problem than raw search.
So if we bring this all together for the researchers and engineers listening, what's the big takeaway here?
I think for a while, the industry has been obsessed with bigger and bigger context windows. The thinking was, if we just have a 10 million token window, the agent will remember everything. SkillRL suggests that might be the wrong tree to be barking up.
Or at least a very inefficient one.
Right. More context is more noise. Intelligence is really about compression. It's about figuring out what to ignore. So if you're building an agent, maybe the question isn't just, how do I store more logs, but how do I curate experience?
Is my agent just recording what happened, or is it synthesizing a lesson from it?
Exactly. And the fact that a 7B model can do this so effectively is the most exciting part. It means that learning how to learn, organizing experience into these abstract skills, can let smaller, more accessible models punch way, way above their weight.
Which leads to that final, pretty provocative thought. If a 7B model can beat GPT-4o just by organizing its experience better,
what happens when you apply this SkillRL architecture to a frontier model, a GPT-5 class model?
Are we getting to a point where the learning architecture itself might matter more than just raw model scale?
It's the big question, isn't it? If the model can write its own manual and that manual gets better every single time it fails, the feedback loop there could push performance ceilings way higher than we think.
A shift from big data to smart data. Well, for anyone building the next generation of agents, maybe it's time to teach them how to write their own rule books.
I think so.
Thanks for listening to AI Paper Podcasts. We'll catch you on the next one.